So here, let's take a look at a sample problem about the evaluation of the electric flux or the net flux. Okay, so here it says a Gaussian surface in the form of a cylinder of a radius r immerses in a uniform electric field with the cylindrical axis parallel to the field. Okay, what is the flux phi of the E field through the closed surface? So here we have the E field pointing to the right side, and the magnitude is uniform. So you can see E field, E field, E field pointing to the right side. Okay, and then here we would try to assume that its Gaussian surface is a cylinder. Actually, I would like to highlight that a Gaussian surface doesn't necessarily to be a physical surface. It is just an imaginary surface. It doesn't necessarily need to exist in a physical form. Okay, so but here we try to draw it out as a cylinder. Only as this. It doesn't necessarily to be a plastic one or a metal one. It's just an imaginary surface, and then we try to calculate the electric flux over this closed surface, and that's it. For Gaussian surface, the only condition is the surface is closed. Yeah. Okay, so here we try to determine the E field over this surface. So let's try to write it out, the definition. The net flux is the closed integral of E dot dA. And yeah, so for the integral, we can separate into three parts. One of it is part A, and other part is part B, and other part is part C. So what is part A, part B, and part C? So you can check it on the figure. So this small a means this surface is part A, and this surface is part C. And for part B, it should be this side part of the cylinder. This is part B. This is B. This is B. This is A. This is C. Okay, so let us determine one by one. So E dot dA for part A. So here, we don't draw a circle here because for this part, it is the original definition for the net flux for the whole Gaussian surface. So we have a circle here, but here, when we consider part A, part B, part C, which means this part, and this part, it is not closed anymore. So we don't draw a circle here. Okay, so for part A, you can see the E field is pointing to the right side. So let me erase it so that it's clear. So for part A, the E field is pointing to the right side. Yeah, and then dA, it should be pointing to the outside and then perpendicular to the plane, which means that the dA should point to the left side. Here, as E is uniform over the whole surface A, which means that E dot dA is negative EA, because here the theta is 180 degrees. So cosine of theta is -1. Okay, so this is the reason. Okay, so and for part, maybe we can determine part C first. So for part C is the y side. So the E field also points to the right side because E field is uniform over the whole space. And then here, the dA points to the outside and perpendicular to the plane. So dA also points to the right side, which means that it should be E times A. Here, theta is 0 degree. I don't try to detail. Yeah, so here, the last part is part B. Integration of surface B for the E dot dA. So here, as much as E is pointing to the right side and dA is perpendicular to the plane, of course, this plane is not a, yeah, this surface is not a plane. It is the sine of a cylinder, but all the dA are perpendicular to the surface B, and of course dA point to different direction for different point. For example, for this point, dA pointing downward, and for this point close to us, this is pointing out of the page, and for the point inside, it is pointing into the page. But no matter which point, dA always perpendicular to E because it is perpendicular to the surface. So in this sense, E dot dA will be 0. So this one is also 0. This is theta equals 90 degrees. So when we try to plug in this one back to here, we can quickly find that phi is negative EA plus 0 plus EA, which is 0. Okay, any questions? No questions. Then we have another sample problem, which will be more difficult, of course. So here it says a non-uniform. Of course, this is non-uniform, so it makes the things complicated. Okay, a non-uniform E field given by E equals this one. So 3x in the x direction, and then plus 4 in the y direction. Y direction, IJK. J hat should be in the y direction. P is the Gaussian cube. So this, we define this cube is the Gaussian surface as shown in the figure. So E is in N over C and X is in meter. So what is the electric flux through the y phase, left phase, and top phase? Of course, we try to calculate the electric flux for the y phase first. Okay, so here we try to calculate integration of E dot dA for the right surface, which is actually this one. This is the right surface. Okay, so of course we need to do some calculation. So the calculation is like we need to determine the E field here, and of course the E field parallel to dA. So the first thing we can quickly determine is dA, the direction of dA. The direction of dA should be pointing to the right side because this is, yeah, this is pointing to the, yeah, this is, this plane is on the, yeah, it's on the right Z plane. It's on the right Z plane with a constant x to be 3 meters. This is x to be 1 meter, which means the side is 2 meters. And this is a cube, so 2 meters for this side, 2 meters, 2 meters for all the side. Okay, so we can write dA to be dA is the magnitude, the scalar, the area of this area. So this is dA times this is positive x-axis, so it should be I hat. So we can write dA to be I hat. Okay, so in this case we can write it as E would be this one, 3xi plus 4j. And here for this plane, x is constantly 3, which means that it should be 3 times 3 I hat plus 4j hat, and then dotted with dA, and then I hat, okay, like this. And then for the right face. Okay, so of course this is a vector, and then we calculate the dot product. And maybe I have not mentioned is that what is the dot product for the unit vector in Cartesian coordinate. But of course, this is pretty simple. Maybe if your mathematics is good enough, you should already know it well. So if we have I dot I, it should be 1. If we have j dot j, it should be 1. If you have k dot k, it should be 1. If you have two different unit vector in different direction, then you always have 0, like this. Okay, so we only have unit vector, the same unit vector dotted together to get 1. Otherwise, you will get 0. So it means that this is dot product. So you can distribute. This is I dot I. So we have 3 times 3 is 9. And then I dot I will be 1. So we have dA for the right face. And then this is j dot I hat. J dot I hat will be 0. So we don't get this part because this one is like, maybe I can write one more step, which is like 3 times 3 I hat dot I hat dA, and then plus 4j hat dotted I hat dA. So I just swap the order of dA times I hat. So we have I hat dA, I hat dA. Okay, so here we have I dot I. This one will be 1. This one will be 0. So we have integration of 9. 3 times 3 is 9. dA for the right surface. And then here, this is just 0. Okay, plus 0. Okay, so here, we just integrate a constant over the whole surface, which means that it is like 9 times the surface integral of 1, which means that we only care about the surface, the area of this surface. The area of this surface is nothing but 2 times 2. The area, A, equals integration of dA, which is 2 times 2, which is 4 meter squared. So it is 9 times 4, which is 36 Newton dot meter square over Coulomb. Okay, any questions? Okay, next. So we try to calculate the electric flux for the left surface. So the left surface is this one. So similarly, we can determine dA point to the left side, which means it is a dA times negative I hat. Okay, so this time we can go quicker because most of the points are similar. Okay, so here we try to determine E dot dA for the left surface. So here integration of 3x. So for the left surface, the only different point is x to be 1 rather than 3. So we have 3 times 1 I hat plus 4j hat, and then times should be dotted with negative I hat and then dA for the left surface. Okay, so here I dot I will be 1, so we have a negative 3 times 1 dA for the left surface. And then this is j dot I will be 0, so we don't have the second term. Okay, so here we have a negative 3 integration of LdA, so it is negative 3 times 4, which is negative 12 Newton meter square per Coulomb. Okay. So most of the stuff are similar, but the only difference is that this is 1, and the difference is this dA is dA vector is a dA times negative I hat. Okay, so we do the similar calculation. Okay, so for the third part, this one is the top surface, which is this one is the top surface, and of course the dA pointing upward, which is dA times ij j hat like this. Okay, so here we would like to determine integration of E dot dA for the top surface. So similarly, so this is top, and then we have 3x. Okay, now we don't really know what is x, because x is changing. Okay, but soon we will find that this is not a great issue. But of course, this is the this is due to, for this one, it is not related to x, and then this direction is not related to x. So so here you can find that you still do the same thing. We do not know what is x yet, but here we have I dot j. I dot j is 0, so we don't really care about what is x. Otherwise, if it is still I hat, maybe for example, if we have an x here, then we will need to do some integration over x. Okay, but here I dot j is 0, so this term vanished itself. Okay, so so the next part is j dot j will be 1, so we have integration of 4 dA for the top surface. And then we can write it as a 4 times integration of T surface and then dA. So the area is 4 meter square. So 4 times 4, which is 16 Newton meter square per Coulomb. Okay, so these three ABC question are similar, but I hope you can understand. This is a simple example to show the idea of calculating simple surface integral. We don't necessarily need to use some complicated way to do the integration. We just assume the E field is uniform over the whole surface, so that all the thing is like integrating a constant over the surface, and integrating a constant like a simple product. Okay, so if no question, then we'll talk about the most important part of this chapter, which is the Gauss law. And maybe it is difficult to understand, but so this is Gauss law, and it says Gauss law relates the net flux of the electric field through a closed surface or a Gaussian surface. to the net charge that is enclosed by that surface. It tells us that it is like epsilon naught times the net flux equals Q enclosed. So in the previous slides and the previous two sample problem, it assumes that you already know how to calculate the electric flux. So if you can calculate the electric flux, then this thing you already know, and then this equation or this Gauss law tells you that this is epsilon naught. Epsilon naught is 8.85 times 10 to the negative 12 power. So it's a constant. Constant times this net flux equals the charge enclosed by the Gaussian surface. So it's that simple. Something like the Newton's second law of motion. F equals ma. If you know two of them, then you can calculate the last one. Here, of course, Q epsilon naught is a constant. So you can either know or Q enclosed, then you can determine phi, or you can know phi and then you can determine the Q enclosed. So actually, this is a form of the Gauss law, just like the product of epsilon naught and phi will be the Q enclosed. But usually, we will not use this form of Gauss law. Rather than that, we will use a form which looks more complicated. And of course, previously, we already know the net flux is a closed surface integral. Closed integration of E dot dA is the net flux. So rather than writing it like this, we usually use it like this. So epsilon naught times this closed surface integral of E dot dA equals Q enclosed. So this is the Gauss law. The Gauss law we will frequently use not only for this chapter but also for the latest chapter. So I hope you can really understand what it is. Otherwise, you'll get lost very soon. Yeah, for the coming few chapters. Okay, so this is the Gauss law. Like the Newton's second law of motion, this is used for high school student. And usually if it is useful, you will write it as F equals m times the second derivative of the displacement with respect to time. Then yeah, if we make use of this one, then we can write some differential equation to solve. And it makes the Newton's second law of motion more useful. And so as the Gauss law, if you write it like this, then it will be more useful for solving complicated problems. Okay, so here it tried to tell you something. So it says two charges equal in magnitude but opposite in sign. So you can see this is one charge. This is another charge. So maybe you can call it, this is plus Q. This is negative Q. Maybe I use another color so that you can see it more clear. I use red color. So this one is plus Q. This one is negative Q. Okay, so you see within this space we have two charges. This is plus Q, this is negative Q, with the same magnitude but opposite sign. Okay, so here electric field lines are also drawn. So the electric field line always starts from the positive charge and ends at the negative charge. So it is like something like this. Will be like an apple, but yeah, the outer part doesn't really show here. But if it's also shown the outer part, then it will somehow look like an apple. Okay, so here it defines four Gaussian surfaces here. And as I mentioned, the Gaussian surface is not a physical surface. It doesn't necessarily to be a practical surface there. It is just an imaginary surface in arbitrary shape. The only condition is that it is a cold surface, and we call it Gaussian surface. So here, suppose this is the first Gaussian surface. Of course, in 3D, but here we only draw in 2D. So suppose this one is the S1. This one is S1. So when we try to apply Gauss law for this S1, just say integration also. Just say integration of E dot dA equal epsilon naught in the front, and then Q enclose. And then for S1, so you can try to mark down, oh, this is S1. But of course, for the textbook, it doesn't denote anything. But yeah, sometimes you may denote for S1, you can just write it in the bottom right of the integration sign, so that it specifies this Gauss law is applied for the Gaussian surface S1. Okay, so for this case, of course, to calculate the E dot dA will be troublesome. You need to separate the Gaussian surface into many small area, and then you try to calculate E dot dA one by one, and then you try to add them together with the integration. So, but here you can at least know, of course, epsilon is a constant, is a positive constant. We can quickly determine the sign of this integral, of this surface integral, without any calculation, because we know the Q enclosed of this Gaussian surface. Q enclosed means the charge enclosed by this Gaussian surface. So in this whole space, there are two charges. One is here, one is here. But for S1, the only charge enclosed by S1 is this positive charge. This negative charge is not enclosed by this S1. So when we try to calculate the Q enclosed for surface charge surface 1 S1, it is positive Q. So we can conclude that this integration, this surface integration, is positive. Or in other words, phi 1 equals this one is positive. So it says phi 1 is positive. Okay, so next, if we try to apply the Gauss law for S2, this S2 only encloses the negative charge. This positive charge is outside from the S2, from S2. So here, if we try to apply a phi 2 equals epsilon naught integration of a E dot dA for the surface S2 equals Q enclosed 2, then this is negative Q. This is negative Q. So we can conclude that this phi 2, okay, I think this is not phi 2. Phi 2, I should say phi 1 should be the phi 1 should be the integration. It should be Q enclosed 1 over epsilon naught. But epsilon naught is a positive value. So if Q enclosed 1 is a positive value, this phi 1 is a positive value. So similarly, phi 2 equals Q enclosed 2 over epsilon naught. So here, Q enclosed 2 is negative Q. So this is a negative value over a positive value. So this is negative. This is positive. Okay. So we can also conclude that phi 2 is a negative number. And for S3 is this one. S3 is this one. So it encloses nothing. So if we try to apply the Gauss law for it, so it's like epsilon naught integration of E dot dA for S3 equals Q enclose 3. So here it encloses nothing. So this is 0. This is 0. Okay, so this is 0. So we can see that phi 3 equals this one, which is Q enclosed 3 over epsilon naught, which is also 0, which is also 0. So we can conclude that phi 3 is 0. Okay, so similarly for S4, S4 is the biggest one, like an egg, the S4. So here, when we apply the Gauss law for S4, it is like this. S4 will be Q enclosed 4. So this Q enclosed 4 encloses both positive charge and negative charge. So this Q enclosed should be plus Q plus negative Q. Okay, which is still 0, which is still 0. Okay, so by this equation, we can see that phi 4 will be Q enclosed 4 over epsilon naught. So this is 0. So phi 4 is also 0. Phi 4 is also 0. Okay, so if you really need to calculate phi 4 by this surface integral, you can feel that, for example, for S3, some of the E field line pointing into it. So maybe for this part, maybe I use another color. Or maybe for this part, this is going into the surface S3. So it contributes a negative phi for the phi 3. And then for this part, this is going out. So it contributes a positive net flux for this part. Okay, but even without calculation, as much as this S3 enclosed nothing, no charges, is enclosed by S3, then we know this negative flux and this positive flux will perfectly cancel each other. It turns out to be 0, phi 3 to be 0. And similar for S4. For S4, you can see this part up to here are all flowing out. These are all flowing out. These are flowing in. You can see this arrow flowing in. So here it contributes a negative value. It contributes a positive value. And here it contributes a negative value. It contributes a positive value. And Gauss law tells you that this positive net flux and negative net flux perfectly cancel each other. It turns out to be 0. Okay, so this is the main part for the Gauss law. So you really need to. So actually, I think you need to remember some definition. For the Gauss surface, we always define the dA to be pointing outside, or the direction pointing outside is a positive direction. The direction pointing inside is a negative direction. And so is the flux. If the flux is going outside, then the flux is positive. If the flux is going inside, then the flux is negative. Okay, so this is the basic idea of the Gauss law. Hope you understand it. And if you have further questions, please feel free to ask me. And